Alright, so basically, just kind of recapping example 7, which I think I did finish for you guys, I just want to make sure. This was an example of a related rate problem where you were trying to find the derivative of the surface area, and they gave you the rate the volume was changing, and unfortunately your formula for surface area did not have volume in it. So you actually had to do two equations that you were looking at and use the two equations and either A, combine them together into one equation, that's option 1, or option 2, go ahead and find the SDT formula and then end up having to find the RDT using the volume formula. So you had like a two-step process in this problem. All right, were there any questions on example 7? Yes, Harvey.
What if we don't know the formula
For
for
something?
anything, like surface area?
I will say that in years before, like in the most recent years, it appears that they were giving formulas on the problem. But I would definitely know basic formulas like volume of a cone, volume of a sphere, volume of any right cylinder prism thing that has a base and a height, which varies the base times the height. I would know those.
If we forget, should we make them up and try and get like dimensional, or would we not use it? What would be the best strategy?
I mean, if you have to, yeah, make something up and hope and pray you get a point somewhere on the problem. But, I mean, try to just, the 4/3 pi r cubed volume for a sphere, cone 1/3 pi r squared, or pi r cubed. So, look them up, study them. I think they'll give them to you, but I don't want to say 100%. Just in case, have some idea of volume formulas. Surface area, if it's any kind of a figure that has sides in terms of surface area, you just kind of go, hey, if it's all the area of the sides added up. If you have the cylinder, just know you cut it and you have the circumference is the width of the rectangle and then the height. And then so that gives you your surface area of the sides and then the area of the base to give that. So you do have to have some knowledge, I think. But like I said, the last few years, I look at like the problem they give you, somewhere in the problem they said, hey, that volume was higher. But I can't guarantee. All right, so let's take a look at the next example, example number 8, and I'm going to duplicate because I want a nice clean sheet of paper. I don't want all this stuff written here, so I'm going to do edit. All right, so let's take a look at example 8, and let's talk about kind of this problem. This is a classic problem that you're going to see as well on your, most of the time these related rates, I have to say, in the last 3 or 4 years, they have not been in your free response. That does not mean that next year somebody writing the test question for the AP goes, woo, I like related rates, I'm going to stick one in the free response. Usually where you see these problems is in the multiple choice, and usually they're in the calculator section. Okay? So that's kind of where you're going to be looking at. And if you'll notice in the homework, when you start doing it, the worksheet for this one, it does say on your worksheet for the homework that you are using your calculator as you wish. And that's mostly because all the multiple choice, you have that option, so you do want to start practicing on it. All right, but still, if you can't set them up, you can't actually do the problem. So let's go through example 8 here with our cars. So we're riding on 2 different roads. They meet at a 90-degree angle, so that's kind of important. In one of these problems, I almost, even though I'm going to read and figure out what they're asking me for, I start drawing it immediately because it's kind of hard to figure out what's going on unless you start having to sketch. So let's come in over here and maybe I'll draw myself. All right, I wanted to be on the board, but since I can't write on the board because it turns my sound off, we will do road number 1 and road number 2. Doesn't have to be technical. Get your roads in there. And a lot of times what I'll come in and do, when I'm talking about roads, we're going to be talking about their distance and stuff. So I'm going to go ahead and add some axes in here that I'm going to be looking at in order to figure out where points are. But they're at a 90-degree angle. The roads do not have to meet at a 90-degree angle. If they meet at a 90-degree angle, I usually like that because that means I can form like right triangles, use Pythagorean theorem, SOHCAHTOA, something along those lines. But if they don't form a 90-degree angle and I have a triangle, what do I look to use? Law of sines, law of cosines, some version of that. Remember, law of cosines is your Pythagorean theorem on steroids for non-right triangles, right? Because, I mean, what is law of cosines? While we're here, let's just remind ourselves. No, that's law of sines. Law of cosines. A squared equals b squared plus c squared. Cosine of angle A or vertex A or however you want to do, okay? You are not going to be given that. You need to know your law of cosines in case they throw you a triangle that's not a right triangle. And why is it Pythagorean theorem on steroids? Because if I had a 90-degree angle right here, what's cosine 90 degrees? 0. So this would go away, and you end up having one side squared plus another side squared equals the third side squared, which is Pythagorean theorem. And if this is 90 degrees, that would make the A the hypotenuse. And so it all works out, Pythagorean theorem. Law of sines. I keep telling y'all to kind of really work on practicing your sine, your trig stuff, because I am telling you, you hate to miss a multiple choice question because you don't know what the cosine of 90 degrees is. That's like just handing it away. Here you go. I missed this question, not because I didn't understand the calculus, because I don't know the cosine of 90 degrees.
0.
Thank you. 0. All right, law of sines. A over sine A equals B over sine B equals C over sine C. Okay? And this is like SOHCAHTOA. If you have a right angle, what is the sine of a right angle? 1. And so when you look at the ratio, one of the sines drops out, and you end up with sine of an angle equals 2 ratio of 2 sides. And it happens to be opposite over hypotenuse every single time. So that all kind of works out for that. So, but going back to this problem, we have a right angle, so I'm using SOHCAHTOA or Pythagorean theorem. How do I know I have a triangle anyway? What else in the problem is going to tell me? What am I looking to find? The distance between. I'm trying to find how fast the distance between them is changing. So I want to find the derivative of the distance with respect to time. But then I also would say, don't we have to have some moment in time when we are interested in this? When am I interested in this? What's my moment, my instant?
When car is 3 miles south, when car B is 2 miles east.
3 miles south, and B is 2 miles east. All right, so that's what I'm actually trying to find. I start filling things in on my diagram. We have car A is 3 miles south, and if you don't remember, north, south. We live on the East Coast. That would be the west, Southern California. Figure out where we are in our little compass. So 1, 2, 3. So currently, right now, the car is here. And then which car is that anyway? That was car A, so we'll label that. And then car B is 2 miles east. 1, 2. We'll put him here, and we'll do this. Now, I am not going to walk in here at this point, and I am not going to label this 3, and I'm not going to label that 2, because they're not constant. That's the instant. I got to start finding some variables to put into this problem before I start worrying about putting the instant in. I am going to put the variable equals 3 at some point, but I got to figure out a variable that I'm looking at, because it's not going to stay 3 forever, because what is the car A doing? It is moving. And which way is car A moving? North. So they're headed this way at some rate. What's the rate they're moving this way? Well, I gotta know. I don't want to. A is not a variable. A is just the name of the point. What do you want to call this variable here? Maybe I should. Yeah, let's go with y. It's on the y. It's like vertical. Let's call it y. All right. And then over here, and I'm gonna move over just a little bit. And since I want to put the instant in, I'm gonna go y equals 3, my variable, and then the instant. And then over here, what do I know about my rate? All right, what's the name? How do I write the rate in calculus terms? dy dt. Now let me ask a question here. Before I say 40. What do I have to do before I can say it's 40?
What? It is increasing.
Is y increasing?
Yes.
As my car physically travels from this location going to the north,
No.
it's decreasing, right? Because as I get closer and closer to the intersection, I'm using y not as y, the y coordinate of a point. I'm using y as the distance between the car and the intersection. What's happening to it? It is decreasing. And if it is decreasing, what's my rate? Negative 40 miles per hour. Okay? Be careful about that. Could I have defined my variable and my instant in time differently? Yes. I could have said y is the actual y coordinate of the point, which would be what? Say that louder. Somebody back there? Negative 3. I could say the instant is y equals negative 3. I do it as a coordinate, and what happens as I'm moving in this direction? It's getting bigger than I could do pi, but look, the whole thing kind of relates. But it makes more sense in this problem because trying to find the distance between, then I'm going to go with the distances from the intersection and distance between, so I'm going to do it this way. All right, then I come over here and I look at b. What do you want to call this variable? X. What's the instant I am at? 2. And is this one, which way am I traveling for b? Where's his rate going? He's going east. He's traveling east. This is also called other reason why I might miss calculus problems, reading failure. Read the question so you know what they're asking or they told you. Don't just assume, oh, they're both traveling toward the intersection. They're not both going to the intersection. One's going to the intersection and the other one's going down the road away. All right? So my dx dt, what is my dx dt? How fast is he going? Positive 50 miles per hour. Okay? And then I'm trying to find the distance between them, so it might be a good idea to go ahead and draw in the distance between them. Label that with my variable d. Because little d is the derivative that I'm using. I'm trying to differentiate, making a pun, between differentiate between little d and big D. Because little d is different. Yeah, okay. I tried. Because differentiate means two different ways. I can differentiate like calculus, or I can differentiate between two quantities. Okay. All right, so I labeled it as capital D. All right, so what do I do next? I have drawn a picture, figured out what they're asking for. I need an equation relating my variables. My variables are x, y, and d, right? Oops, sorry. D squared equals x squared plus y squared. Equation relating my variables. This is why I want to stress to you, when you were drawing this problem, why did I just not go 3 and 2? Because then I start to look for a formula relating my variables and forget I actually have variables. So you go variables first. Put your instant on with an equals right next to it, and you know that's the instant that you're looking at. And then you get to this part, and you're like, fine, what are my variables? X, Y, and D. How do I relate them? Pythagorean theorem. Now what? Find the derivative. We don't have to solve or anything like that, because we have this nice little implicit. Derivative of D squared. The derivative of D with respect to T, right? Chain rule, implicit, equals 2x dx dt plus 2y dy dt. And so now, once I take the derivative, here is my related rates formula. the formula that is relating the rates I know to the rate that I want to find. Do I know everything in this formula? Okay, so I know x, I know y, because I'm at that instant. I know dx, dt, dy, dt, but I don't know d. So I have a little question mark here. I need to know d before I can actually plug and chug. But I go back to my picture and I say, do I know d at that instant?
Yeah.
I don't.
You just find it.
So find it. That's all. That's what. When you get to here, if you got something you don't know, you go, wait a minute, go find it. Square root of 13. So I add that into my instant. And then we plug and chug. 2 square root of 13. The derivative of the distance with respect to time. 2 times 2 times 50. Plus 2 times 3 times, what are we at, negative 40? Negative 40, and then from there, you do arithmetic. I'm going to skip that in the interest of time and just tell you the answer. First off, let's do a common sense check, gut check. Is the distance getting bigger or smaller? As B travels this way, B is going away from the intersection, A is going toward the intersection. I'd say my gut check would be, I think it's getting bigger. Okay? Because he's going faster away from the intersection, and this person's going towards, I'm thinking bigger. So what does that mean this number should be? Positive. Is it? Oh, it's not. Our gut check didn't work, did it? It actually does end up being negative. Why? I know, I want to be like, it should be. It should be.
It's because they get closer and then farther. At a different
Yeah, there might be, a question that they would be interesting. I don't think they'll ask you this. What is the maximum distance between them? Could we turn this into an optimization problem almost? Sure, because the rate that you're traveling, the distance is changing. There could be a maximum distance they are apart or closest distance they are. We could turn it into optimization. We won't do that. It ends up being actually negative 20 over square root of 13. So at that instant, that must be at a point where they are moving closer together, but then at some point they'll probably move farther apart at some other instance. Okay?
This is why it's so vital to have an instant.
That's why it's so vital to have an instant, so I know when. And I'm not done. I can't just walk away. I can't. Thank you. Miles per hour. Okay. Miles per hour. I haven't answered the question yet. That's the next thing. Good job. I have an answer, but what do you have to actually do with the problem? Write the sentence. So, when, what was my instant? Yeah, it's 3 miles south, and B is 2 miles east. It's just a lot to write, kind of tedious, but you still got to put it. When, what, the distance between is decreasing at 20 over square root of 13 miles per hour. And we will get our right. Everybody good with that one? All right, let's go to the next problem.
This one's long.
The sand problem. Lovely, lovely sand problem.
Is this like a classic?
Yeah, they like to pour sand and stuff and make all sorts of figures. This is what it is.
Do they make bears?
I'm going to draw my picture up here so I can save some space. Here's my little cone. Oh, I don't want this. Make it a little shorter. Here's my little cone of sand coming in. No, because when I have a little conveyor belt up here, I have sand.
I was thinking it was a cone.
Okay, sand pouring down. Why does it make a cone? Because there's some kind of friction kind of thing going on, some kind of little science-y, physics-y kind of thing, right? Which we'll actually talk about down here at the bottom. That when you have some kind of granular material, that when you pour it, it slides down and it will form an angle on a tip because you're making up a pile. Okay. Sounds hard. It's not too bad. All right, so we're pouring it. We're creating this cone. Okay, a couple information we want to start putting on our picture. Your base diameter is always twice your height. Which is a fancy way of saying what about your height? It's the same as your radius. So in this picture, well, not always true, but in this problem, yeah, in this problem, they are saying that. They may choose some other version on that, but in this problem, they are saying that our radius and our height are going to be the same. So I might make a note to myself, h equals r up here. I'm going to go ahead and put them both in there because looking ahead, I am looking at how fast the radius is changing, so that's dr dt. And I'm looking at how fast the diameter changes, that's the derivative of 2r with respect to t. And I'm looking at how fast the height is changing, so it might be kind of important to remember that the height is the same as the radius. Sand's being poured at a rate of 20 cubic inches per second. What are they giving you there? dV dt, because that's cubic inches per second. That must be a volume, dV dt. And the height, when the height is 6 inches, so that's my instance. And so let's do part A. How fast is the radius of the tile change? Oh, I have an instant. Height is 6 inches, so let's put that in right there. So I have a variable and an instant. All right, what am I looking for in A? dr dt. And when am I trying to find this? When h equals 6. And what was I given?
dV dt.
dV dt and volume. What's happening to my volume as I pour sand? Increasing, so my rate is positive. Inches cubed per second. Do I know a formula between, what are the variables there? Volume, radius, and height. What is the formula for volume, radius, and height? Almost.
Squared.
Nope. Pi r squared h, because I get cubic inches, so I can't have r cubed h, because that would give me inches to the fourth. Right, so a little dimensional analysis there. They are. So we have that. But do I really want that as my formula? I can take the h out. Why can I take the h out? Nope. I don't want to plug in an instant yet. I haven't related anything. It's r. You're not allowed to plug in instants until after you get your related rates formula. Okay, so volume equals 1/3 pi r cubed in this problem. All right, now that I have a formula, what do? Take your derivative, dV dt equals pi r squared dr dt. So I get my formula relating the variables. I now have my related rates formula. Do I know everything I need to plug into this fancy little related rates formula?
Yes.
I know dV dt. I know r, because that's my instant. What am I looking for? dr dt. So I have a little algebra to do, but that's fine. I plug before I solve. It's easier, put the numbers in. So dV dt was 20 pi. My r is 6. And then dr dt. Now, I've been kind of doing something bad here, and I probably need to start putting this in. So I'll do it right here. When r equals 6. This is that math communication thing that we want to be very, very careful that we don't kind of get dinged on. This is a formula. This and this are not equivalent to each other. This has to do with that thing where if I had f of x equals or f prime of x equals 3x, and then I want to go, hey, I want to figure out the derivative at x equals to 1, and you guys, oh, that's equal to 3 times 1, will they ding you for this? Because this is not f prime of x, that is f prime of 1, and so you'll get dinged because you have poor math communication. So it's a, oops, I said 1, there you go. So I have poor math communication. So you want to make sure you're labeling it, and you want to be careful that when you are doing these things, this is the formula, and then you're plugging stuff in because you're at an instant. So a lot of times you either need to save this. If you are, if it's nicely already solved for dRdt, you could go over here and go the little line. You remember the little line notation we were using? R equal to 6, like that. So that you say there's some indication that I'm finding this when R is 6. Question, Harvey?
I was just wondering what happens to the 1/3.
When you take the derivative, 3 times a third is 1. Pi r, subtract 1 from your exponent, 2 times derivative of r. Chain rule. Power rule, chain rule. Okay. All right, so everybody okay on that? I'm bad for it too. I have a very bad habit of getting to here and going, plug in, yay, and I plug everything in. You got to say when, or you have to put something in it to show that I'm doing it at r equal to 6. Okay? This or this, one of them. All right, and then solve for your answer. dr dt when r equals 6 is equal to, I end up with something weird, 5/9 pi. What are my units? Inches per second. And then we answer the question, when, oh, and I kind of glossed over this. They're giving you the height as 6. But since height and radius are the same, we're going to do that. So down here I would say when height is 6, answer the question they asked you. When the height is 6, the what? The radius is increasing at 5/9 pi inches per second. Well, we have to do it, but we know the answer. No. You answer the question. If there is a free response question, even if it is easy, well, yeah, your reasons you've already got. Yeah, right. All right, hold on. Just we'll get there. Let's do B. You're looking ahead. We'll cross that bridge. All right. What are you asked to find in B?
Is dD over dt.
The D, we'll use that for diameter. dt. D is diameter. I don't have it labeled anywhere, so I do that. When height is 6. Now what's your gut feeling on this? What's your gut feeling? All right, well, let's we have 2 different answers in my gut feeling, so let's see. What do we know about D? What is my formula relating my variables? D equals to R.
H equals R.
And H equals R, so also known as D equals to H. But I'm going to go ahead and use this one, because I just found dr dt. What do I do with the formula after I get a formula relating the variables? Derive it. The derivative of the diameter with respect to time would be 2 times the derivative of r with respect to time. Now can you answer that question, and I don't need a gut feeling. How is the rate the diameter is changing related to the rate the radius is changing? It's twice. And we already know this, so plug and chug. The derivative of d at this time is equal to 2 times what I got above, 5 over 9 pi. What are my units? 10 over 9 pi inches per second. And I don't actually need to do an instant for this one.
Wait, you don't?
Oh, yes, I am using an instant value. I still do. Darn.
You use that.
Because I used this, and this is only when. So when h equals 6. Can I just leave the answering of the question to you? That's fine. Let's go to C. What are we trying to find in C? Find the h dt when h equals 6. What? Yes, your gut feeling is you already know this answer, and you do. But why do we already know this answer? What is the... Yep. The equation relating my variables is h equals r. What is your derivative of that? dh dt equals dr dt. So, when h equals 6, dh dt equals 5 over 9 pi inches per second. And you can write the sentence. What is that for you to do? Yes.
Is it not going to change the lowercase h and the
Yeah, technically I probably should. They probably give it to you on that because there's no other h, but let's be precise and change that to match my picture. In my own defense, I can't see my picture when I'm zoomed in. So if I was doing this on my own paper, I would have my picture in front of me, and I would not make that mistake. But all right, we good? We ready for D? D is asking, okay, the angle of repose. The angle of repose, kind of a little bit, is the steepest angle at which the sediment is stable. The angle of repose,
If it's too great, does it just explode?
no. All right, so my angle of repose is that angle. We're basically saying that's the angle that, because of the friction of the sand and the physics of the problem, is going to be the angle that it slides down to. Okay? And that's the angle at which it is stable.
What would, like, if it was too steep, what would it do?
You would just like it.
The sand would slide back down until the angle becomes the same angle of repose. There is a certain angle at which it's stable. If you pour more on, it slides down the sides and makes the same angle again. Okay? It's based on whatever the properties of the granular thing that you're pouring at that time. Okay? Now, let's do a gut check here. And I'm doing this because you can answer the question, but remember you have to always use what to answer the question in a free response. Calculus. So the gut check goes for the multiple choice. If I can get you to get the gut check right, you're running a little short of time. You go with the gut check and you alrighty, I can answer this question. I don't go to work for it. But if you're doing this in a free response, you must have calculus. Okay? So gut say, I think this doesn't work. But what do you think the answer is to the question, how fast is it changing?
Going to be decreasing, because if you're pouring on more sand, then it's always going back down.
The angle's stable. That's the point. What do you think the rate's going to be? The point is it's supposed to be 0. It's supposed to be the rate when you pour it down. It's supposed to be stable. Not changing. Stable. Not changing.
But it doesn't say it's
Well, not if you're in a pre-response question, because you have to have what for your reason? Calculus! We got to go. Hey, it's 0 because I think it is. That's not a valid reason. All right, so now we're going to do the calculus part. All right, you pretty much already should know the angle. I'm just going to bring my little picture down here for a moment. And it doesn't matter at what instant I am in. Aman, wake up. Sit up. Yeah, try to be like I'm awake this morning. Good. I can sleep on my snow day. Why is it gonna be 45? No matter at what instant I am. H and R were equal to each other, and the only angle in a right triangle for which the two legs are equal angle is 45. So the first question was find the angle of repose. The angle of repose is 45 degrees because, and this isn't really calculus, this is just basic trig. What do we know trig ratio wise? Ryan, you're annoying me.
R and H are the same.
I know they are the same, but what trig?
It's a 45, 45, 90.
Tangent of theta equals h over r, which equals r over r, which equals 1. There you go. There's my reason. What angle has a tangent of 1? Trig! Trig ratios. Learn your trig ratios for the love of God. Learn the trig ratios. Yeah, technically, I guess, technically, if we go by what I said earlier, calculus prefers radians, so we should say radians. So other than that, we'll make that change. Wait, your calculator, radians, calculus, radians, put everything in radians. So what work was in degrees?
Wait, I think it could have been.
Okay. But I haven't answered, when we answered the question, we think the rate is going to be 0. They're really asking you to find d theta dt. You can do when h equals 6, but it'll actually be for all of them. We can save that instant if we so desire.
Since we already have this equation up here.
We have an equation that relates them. Tangent of theta is equal to 1. What do I do with the equation after I get it? I derive it. How do I derive it?
Squared theta equals 0.
Yeah, derivative of tangent is secant squared theta. D theta dt, good catch, equals 0. Does it matter what secant squared theta is?
No.
We already know theta was 45, and so this will end up being 2, as long as it's not 0, which it can't be because it's a secant. Is anybody puzzled by that statement? Why can't the secant ratio be equal to 0? Because it's a reciprocal, because the range of the secant function is negative infinity to negative 1. Skip the middle, 1 to infinity. Valid secant ratios are only bigger than 1, smaller than negative 1. You up, you down. Trig. That can't be 0. So I didn't even need to know the angle, because if I divide that to the other side, I'm good. I'm not dividing by 0. I end up with the theta dt equals 0. At that instant and every other instance. The angle is stable. It is not changing. So if you were not convinced that the angle is stable, I'm convinced you now. It's not changing. Alright? Everybody good? Alright, next problem. Oh, the sentence? Oh, yeah, we should do that. We should do the sentence. Well, you could say when, but they said how fast is it changing? How fast is it changing? The angle of repose is never changing. You could, I mean, I was trying to go because I was getting ready to say increasing or decreasing. So, but it's not increasing and it's not decreasing. So you say never changing. I would just say because the rate is 0 radians per second. And I don't need an instant because it's always. So I put never in there, so I'm taking care of that. I don't say when. If you said when, that's fine, but it's really when our height is anything it wants to be that's valid, the angle is going to be 45. All right. Next one. Oop.
Skip one.
Example 10.
Cherry flavored snow cone.
Cherry flavored snow cone.
Oh, I hate it when they do that.
per minute. Yeah, let's do cubic inches per minute. What am I giving you?
Volume.
That's on your volume. VDT, the derivative of the volume. Okay. The paper spends roughly is 2 inches, and the 5 inches total. Yeah. When the depth is 3 inches, and the questions are going to ask. Yes.
Does the AP exam like cones as much as we do?
Yes. There will be a problem with a cone somewhere on the AP.
I mean, we've had, this is our 10th problem and we had like 4 round cones.
Okay, it is what it is. Okay. So I'm going to start drawing the picture. I mean, in A, what are you looking for in A? The RDT. Okay. So I'm going to start by drawing a picture for this one. And obviously my snow cone is melted enough. Make this little oval shape for the top of my paper. I'm drawing the paper right now. There's the paper cone that the snow cone comes in. Okay. Now I want to ask a question about this before I start labeling some stuff on here. Is this changing?
Nope.
Do not call that R. That's not changing. Your paper that you get not magically changing shape for you. This is going to be, what is the radius of the top of the paper cone? 2. Just label it a 2. It's not a variable. It's a constant. It is the same number for the whole problem. Do not make variables for constants. It's constant. 2. What else is constant in this problem? The height. Put that in. That's going to be, what was it, 5? 5 inches. 2 inches. So you put constants. It's like the ladder. The ladder was 10 feet. You didn't put L or H for hypotenuse. You said, hey, it's 10 feet. Done. This is 5 and 2. Done. Okay, we are looking at the melted cherry mixture. Okay? This is where I have to have my variables, because that's what's changing, right? The little cherry mixture inside is leaking out the bottom. There's little drops down here. It's leaking out. Okay? So we must have this little cherry mixture inside here. Now, where am I putting my variable? Is it okay to put an R there? Is that changing? Yes. Okay. What else is changing on this? The height or depth, what do we want to call it? Let's call it D for depth. Of that is changing. So I make those variables. Because that's leaking out. That's what's changing. That's what's changing. The snow cone shape of the paper is not changing. The stuff inside is changing. Leaking out. All right, so I have my picture. Yes. It's all right. If you want to, we can do... You want to use an H? That's fine.
What's wrong with H's? What do you have to use H?
H is my favorite letter.
H.
Wow. Oh my God.
All right. Now what do? What's A? I'm asking for dr, dt. What are my variables? HR, V volume, because this was something related. Maybe I should put down what I'm given. We're trying to find dr dt when H equals 3, and I'm also given, let's do our dv dt. Everybody good with the negative part of that? Why is it negative? I'm leaking out, so the volume itself is getting smaller as it leaks out. So we have negative there. All right, so my variables are V, R, and H. So what is my formula relating my variables?
V equals 1/3 pi r squared. We're going to have this formula down. The only one we know.
Is my V. Or that one is 4/3 pi r cubed. Here. Here. I have two options. Two options here. I can take the derivative right now. All right, let's talk about our options. Just take the derivative. When I take the derivative, what will be in the derivative when I get it? I'll have a dv dt, a dr dt, a dh dt. Okay, and I will have maybe an r. The h will go away, but no, I might have an h and an r still in there. All right. So I would have lots of stuff to find. Option one, just take the derivative, and then I have to go to the instant and go find a bunch of stuff. What's option two? Find some relationship between R and H that I can substitute in. So I can just get rid of the H so that I can just find dr dt. Yes. You can't put an instant in. You can't put an instant in until after you get the related rates formula. That is only the height of that instant. Because if I were to take the derivative of this, and this is why, this is a mistake, classic mistake. Everybody listen. If you try to plug in the instant before you get the rates in there, when I go to take the derivative of a constant doesn't affect anything. If I were to take the derivative here in this formula, shouldn't there be a dH dt somewhere in there that has to be accounted for? You're not accounting for the fact that you got to get the rates related before you put the instant stuff in. Never plug in instant stuff at the beginning. Sure. Let's take a look over here. I'm going to draw this. I'm going to make it in green here.
Can you make them like similar snow cones, similar cones, and then compare the height and radius?
Well, if I pull this out, let's take a look at this.
Yeah, basically along that line. That's
Two
simple.
R, this whole thing is 5, and that is H. Classic calculus, overlapping right triangles, no, not overlapping right triangles. They are similar triangles, and if I have similar triangles, I can set up a proportion. I can do R is the 2 as you can do multiple ones. That'll all work out the same. R is the 2. H is the 5. Little to big, little to big. Could I have done R to H equals 2 over 5? Yep. It all comes out the same at the end. Because what am I trying to do? Get rid of H. H is, well, let's do 5 halves R. Okay? 5 halves R. So we're going to choose option 2 on this. Instead of option 1, take the derivative and then go find all the stuff, I'm going to go, it'll be really a lot easier if I just plug in the R. So this is going to then turn into V equals 1/3 pi R squared 5 halves R. And let's simplify, because simplify early and often before I do the derivative. 6 pi R cubed. And that is actually even way easier to take the derivative of, because it's just power rule. So it's a good thing in this problem. We will show some examples where it's not always a good thing to do this substitution. But I would evaluate it. I would say, I'm going to see if making that substitution is going to help me. Right? Regardless of whether I made the substitution or not, I will still have to use this fact to find information. Because when I get, after I take this derivative, if I don't substitute the H, I'm going to have an H I have to find at that instant. Well, how am I going to find H? Well, I'm going to plug in the R equal to, well, the H was 3. That's the instant. How do I find the R? Oh, I'm going to use this little formula. So I could find everything I need, but I don't want to have to do that. All right, so I'm going to come over here. What is dv dt? 5 halves pi R squared dr dt.
You can find it
But that's okay. Remember, at the instant, can I find R? Let's come back over to our instant. Anything you don't know that you need, you got to go back to your instant. So right now, do I know dv dt?
Yes.
Yes. I don't know r, and I'm looking for dr dt, so I have to go find r. So I come back over here to the side and go, I want to find r when h is, what's my instant? When h is 3. How do I find r when h is 3? Yeah, you just use the formula you just calculated with the proportion. If the h is 3, then r would be 6/5. Now am I ready to plug and chug? So when h equals 3, dv dt, oops, no, that's the one I know. What is dv dt? It was -2 because we're leaking out. -2 equals 5/2 pi times 6/5 squared times dr dt. Alright, and then we do some arithmetic, which is simply square, square, cancel, cancel, move it to that side. dr dt ends up being and what are my units?
Inches per minute.
I know. Just happens. Can you guys answer the question? When h is 3, when the height, sentences, when the height is 3 inches, the what? The radius of the cherry mixture is decreasing.
5/9 pi.
There you go. Sure, yeah, if they do that. When I go back to my English depth.
Oh, yeah.
Yeah, when the depth is 3 inches. How fast is the radius changing? Alright, how fast is the melt leaking onto Kieran's clothes? I know I spelled it wrong. He called me on that. I was like, you would think I would know. Kieran. It's C-I-A-R-A-N. I was trying to choose. He's in my second period class. There you go. I'll change it to an A for him as he's watching the video. Alright. So, think about this. What are they asking me to find now? How fast the melt is leaking onto his clothes.
How fast is the volume decreasing? Is that what they're asking? That's how fast it's dripping.
I agree it's related to the volume where it's leaving. I agree it's related to volume.
But, I mean,
What's happening on his clothes? What's happening with the melt?
it's dripping onto him.
It's dripping onto him. Why? Why?
It's negative.
He's accumulating melt onto his clothes. He is not decreasing the melt. The melt is decreasing out of the cone, leaving the cone and accumulating on his clothes.
Unfortunate.
Okay? Yeah, so it's the opposite of. So if you want to, you could say, call it accumulation or something. Pick something to call it. So see, how did they ask the question? The question says, how fast is the melt leaking onto... I'd probably do accumulation before I did anything like that. I would say A, accumulation of melt on clothes. We're trying to find dA dt when H equals, or let's do depth since that's what they were doing. When depth is 3. And all you have to basically go is we know dA dt would be the opposite of dV dt. Do not call it dV dt.
Oh, no, don't call it the ADT.
Yeah, don't call dA dt dV dt. Because dV dt is a negative. You need to get another name because it's the opposite of
So
it.
you feel like what's the opposite of the
Yep,
volume?
because the rate that it leaves
Is the rate opposite of
is opposite of the rate that it accumulates.
Okay.
Very good? So dA dt would be 2, what were our units again?
Inches cubed per minute.
Inches cubed per minute, and you could write the sentence for that. I will leave that for you for the sentence. Alright, so now we're going to add in, the Kieran has a little cup. He's going to be collecting it. He decides he doesn't want leaking on his clothes. So he takes his cup, he's going to put it right here at the bottom. He's going to collect the melt into it. The cup has a 2-inch diameter. Has a 2-inch diameter. Is that constant or variable? Constant, so we'll just go right ahead. And if it has a 2-inch diameter, what's my, don't use a variable. What is my radius? 1. So we'll just put a nice big 1 right there. How fast is the height in the catch cup changing? So as it accumulates down here in the catch cup, all my little liquid down there, where's my variable? The height, we already used H and R up here, so maybe we could do H sub 2, R sub 2 here.
C.
Oh yeah, we don't need another R. Good job, good job. Don't need another R. Good job. Constant. 1. Alright, so we have this second little height. If we want to, we can call depth D, capital D. Let's do capital D. I don't like H sub 2. You know, I'll just do that. D for depth. Alright, what are we actually trying to find? How fast the height is changing? What is that? dD dt. So find the derivative of the depth with respect to time when h, the depth of cone liquid, is 3. What's the formula? What do you think? What do you think? Okay, so this is kind of like the accumulating one.
Yeah.
What is going to be the change in volume down here?
Opposite dVdt.
The opposite of what it was up there. So if it's leaving at 2, it's accumulating at
So it'd be dAdt.
dA dt. Okay, so we could say the accumulation, let's do A, and we have that accumulation of melt on clothes. Maybe we want to say clothes or in cup. Either way. And if you want, you can kind of maybe go, that's also the volume of liquid in cup. Tell them what it is, just be clear. So how do I get the volume in the cup? Pi r squared h, pi, but r squared? 1 squared, or pi h. I did, thank you. Pi d. So now what do? Derivative dA dt equals pi dd dt. Right, we know everything, don't we? Are we ready to just answer the question? So when the depth of the cone liquid is 3, we would end up with 2 equals pi times d dt. So what is d dt? And what are the units? Inches per minute. Okay, there we go. How many more of these we have? I get tired. I get tired.
Do you have a napkin you could copy stuff?
Do I have what?
A napkin you could copy stuff?
No, I don't. Sorry. Okay. Last example then. Is this truly the last example? Oh, because we did the spherical balloon the last time. Okay, that's what it's like. I thought there was another one. All right, the last. A young boy, young boy, out at night, past his curfew. It's running toward a street lamp. Okay.
Bad idea.
Here's my street lamp. Draw my little street lamp. Here's my little boy running. Okay. Nice little picture going here. It's running toward the street lamp, 6 feet per second. The street lamp is 30 feet tall. The boy is 5 feet tall. And when he is 4 feet from the base of the lamp post, I'm asking some questions. Is there any constant?
Big lamppost, he gets caught.
Yeah. The street lamp is 30 feet tall.
Chasing him.
That's a constant. Constants, do not make them variables. Constant, 30 feet tall. What else is constant? No. The boy is 5 feet tall. I don't believe he's changing any. It's not, I mean, not people that don't grow that fast. So we're ignoring that. He is 5 feet tall. His speed, he's traveling this way. I need some variables before I can do the speed, though. All right, so now I've got to put some variables on here. I have my light shining down. Look, I made it yellow for light. Okay. All right. And where's the shadow at anyway? Behind him. So here's my shadow back here. All right, and we're in A, we're trying to find how fast his shadow length is changing.
L.
So let's call this L. It's fine. Should I call this something? When he is 4 feet from the base of the lamppost, let's call it X. And that's a variable, but we know the instant, so I'll add equals 4 to that one. And once I do that, do I know what rate did they give me? Dx dt, and is x increasing or decreasing? Decreasing. He's running to the street lamp, and x is the distance from the boy to the street lamp, so it's getting smaller. So it would be -6 feet per second. Why wouldn't it be what? dv? Well, it is a velocity itself. It's not the change in velocity. It's his change in position. I think x is like his position function. Dx dt is his velocity function. Okay? All right, so question A, how fast is the shadow length changing? What are you trying to find?
DL dt.
dl dt when x equals 4. What are my variables again here? X and
Y. Or L.
X and L. How do I get a relationship between X and L? The similar triangles. See, they started to see a theme on this. Oh, look, I have right triangles that overlap. I can say 5 is to 30 as L is to X plus L. As long as, wait, say that question again? That's fine. We're finding a formula relating our variables, which are changing, which is what we want. Yes.
How do we know that his height forms a...
We're making some simplifying assumptions here. Just go with it. He will always run in an upright position. We are humans. We will assume it's 90 degrees. Just let it go.
No. It's not even that we said that it's 90 degrees. How do we know that the light isn't above his head?
We're going with a nice little. We'll just do that. Just put a little light bulb up there.
No. I mean, like, how do you know that the angle isn't different so that it doesn't actually form a perfect triangle with his height and the...
Because that's how shadows work. Shadow, the light ray hits him, he blocks the light, and he'll get a shadow. That's the way it works. That's the way it works. You do remember I'm recording this, right? Alright. We won't name names. Okay.
Too late.
Too late. Alright.
I fall gracefully.
What should I do now? What should I do now?
Cross multiply.
Yeah, simplify early and often. Do not take the derivative when you have this now. I can simplify this. 5x plus 5l equals 30l. I can keep simplifying. 5x equals 25l. So x equals 5l. Fine. Or, depending on if you wanted to, L equals 1/5 x. Depends on what I really want to find. I don't care. Pick one. Simplify early, simplify often. Now I'm going to do my derivative, because now I need to relate my rates. Got my formula with my variables, relate my rate. Notice I haven't plugged anything in yet because I haven't got my rates related yet. Now, what do you want to do? You want to use this one or this one? Really? I'd use that one. I'm trying to find dl dt. Why not use the one that already has dl dt? L equals. Oh my God, it's constant though. Are you seriously going to be scared by a constant times x? What's the derivative over here? dl dt equals
1/5 dx dt.
1/5 dx dt. Oh my God, y'all and your scared littleness of fractions. Alright, now I pretty much know everything I need now. dl dt when x equals 4. Notice what's true about this problem. How fast is the length of his shadow changing?
Decreasing. 6 over 5.
That's true, -6/5 feet per second. I want you to notice something else about this problem. How fast is it changing when x is 3? How fast is the shadow length changing when x is 3?
Oh, it's always changing at the same speed.
It's constant. It only depends on the rate, on how fast he was traveling. His shadow length, the rate his shadow length is changing only depends on how fast he himself is traveling. It has nothing to do with how far he is from the street light. Weird. We do know that because they said it did not say he is traveling 6 feet per second when he's 4 feet from the base. It said he is traveling 6 feet per second. So that is actually, he's going at a constant rate. Okay? So, yeah. Alright, can y'all answer the question? Alright, and the last part. How fast is the tip of his shadow moving? What are you being asked to find in B? How fast is the tip of his shadow moving? That is not dl dt. I heard, Nick, what did you just say? It is a combination because let's talk about this position, this point, this location, this position. What is my position if I am here where the tip is? What is his position? X plus L, right? So the tip is located at x plus L. So dx plus L, the derivative of x plus L with respect to time. But, oh, does that scare you? Why? Why? Okay, the derivative of a sum is the sum. So, are you scared? No. It's dx dt plus dl dt. And do I know the answer? Because guess what? Did I find dx dt when x equals 4, or any time really, but when x equals 4, what is dx dt? Negative 6 plus, what's dl dt? Negative 6 over 5, which is going to give me, do some arithmetic, negative 36 over 5, what are my units? Feet per second, and the sentence, let's go ahead and write the sentence while I'm here. Want to do that? I could say when x equals 4, but we actually could say everywhere, at all times. At all times. Yeah, that would be true of the first one. I shouldn't say times. It's at all distances from the lamp, because x is the distance from the lamp. Yes. The tip is doing what? Decreasing. I really need a better word there. I can't say the tip. What about the tip? The tip is I need a distance. The distance, let's do the distance from tip to lamp is decreasing at 36 fifths feet per second. You could also say the tip is moving
Towards the lamp.
towards the lamp, closer to the lamp at 36 feet per second. That would work too, probably. Get to 90. No, we have like 15 minutes left. Okay, let's talk about homework and what's going to happen, snow days, and all of that stuff.
Are you recording this?
I am recording. I'm getting ready to stop recording, but
And the other people.
say hi to second period.
Second period. We're better than you.
No,